Hi, this is Mark with a supplementary lecture for the Executive Black Belt, Executive Green Belt class. This is on measurement systems analysis. And what we're going to do is just give a general review of MSA, and we're going to give an application to continuous data. Now, measurement systems analysis, like most things that we cover, is a pretty deep and broad subject. But this is going to take you a long way, and in fact, we'll do a couple of examples. We will use Minitab to do the examples. Anyway, measurement systems analysis is really, in the experience that I have, is in many Six Sigma projects, ends up being a very vital thing, either at the get-go or sometimes even more importantly at the end, to establish best practices or good practices, safe practices, so that you can collect data that you can continue to rely upon. Well, think about it. We're making a lot of, one of the tenets of Six Sigma, one of the principles, is that we want to make decisions based on data. Well, if the data are no good, why would we get up on our soapbox and really talk about why it's so important to make data-based decisions? No, it's really important to have good measurements and to institute those practices in. So measurement systems analysis can be helpful both in the measure phase of a project or often at the end of it. And you know what? It's just darn good, a darn good technique to know in managing, because you can use this sort of paradigm that we're talking about to check to see whether multiple people would end up getting the same answers or some very similar answers if they measured something. Or if the same person would get the same thing twice. So let's take a look at it. After completing this, you'll be able to explain what measurement systems analysis is and what its purpose is. You'll be able to state the difference between accuracy and precision. Now, most of us in everyday life use those words interchangeably. In fact, we use accuracy to mean correct. We have a very specific definition in statistics, and it means that on average you hit the target. So on average it's correct is what it means. On average it gives you the right value. And if it doesn't, on average, then that measurement is said to be biased. So that's what we mean by a biased measurement. That could be either, when we're talking about measurement systems, it could be a scale that's miscalibrated, or it could be that same scale if somebody constantly holds their thumb on it to cause extra weight, like if they're trying to cheat you or something like that. That would be a bias. All right. And we'll actually perform what's called a continuous gauge R&R study. Okay. So the two things that we really want to do are we'll measure. In fact, let me go back to here again and I'll use my pen just a moment. What we're going to look at is we're going to look at what's called an accuracy study. And this is going to be, not study. Oh, I didn't draw that T. There it goes. And we'll talk about a gauge R&R. I don't know why, but usually the U is missing on this one. This one is all about the average, for the mean, and this one is all about the sigma, the variance, the variation. Okay, so those are two separate problems. I can have a measurement system that is riddled with accuracy problems. That is, it's a biased measurement system. That's a big problem. But another potentially big problem is I could have a measurement system where the variation is just so big I can't trust the measurements themselves. Hopefully that makes sense to you. So we're going to look at both. Okay, and here are some places where you can, where this is going to come in handy, I think, where you might use it in a Six Sigma project. Okay, so what is a measurement system? Let's just start out with that. So a measurement system is any piece of any device that's used to measure something, but it's also like it could be a a flow meter or a ruler Certainly that's part of the measurement system, but it includes all sorts of other things. It includes people, it includes the documentation that they might use, it includes the definitions of what the measurements are, how they do them, any procedures, how the data get uploaded to a database, all sorts of stuff. The system involves all of those things. And when we want to fix a measurement system, we have to be able to think about when we look at the data that we get, how do we go about fixing it? And how is that going to tell us, A, that it does need to be fixed, and B, what might work? Okay. And we already talked about this. Without a good measurement system, we cannot make decisions based on data that are worth anything. Okay? So setting up periodic MSA, or measurement systems analysis, is often a key component of a control plan because it helps keep us testing on a monthly basis or quarterly basis to make sure that we are very comfortable when somebody says, can we trust this data? We can say without equivocation, yes, absolutely we can. So what are some characteristics of a good measurement system? First, it's accurate. That is, it measures what it says it's going to measure. Another way of thinking about it is, on average, it gives the right average result. Now, what the heck does that mean? Well, it turns out that if you measure if you have any continuous measurement system, let's use a weight as a weight of a person as something that you might want to measure. If you get on the scale, if you have a home scale or something like that, you know that you can get on the scale, step off the scale, and then step back on it, and you might not get exactly the same weight. It may vary by a tenth of a pound or a hundredth of a pound, or on some cruder scales it might even vary by a pound or two. And you also know that, for example, if your procedure isn't the same, like if you weigh yourself in the morning and you're wearing, just your pajamas and your bunny slippers every morning, and if you weigh yourself at that precise time, that you're more likely to get consistent results or a consistent measurement that you can compare things to than if you measured yourself at any time of the day. Maybe right after lunch, that would be a bad time, or right after you put your work boots on or hiking boots on or something like that. Obviously, the weight of the boots is going to make a difference. So, there's that. The second thing is, so on average, we want it to be measuring correctly. And then the second thing is, we want it to be precise. The fact that it varies a little bit, that's okay. But if it varies a ton, even if it's on average correct, that's not very good. Like, suppose you got on a scale and it said, I don't know, that you weighed 170 pounds. If you're a man, that's maybe not a bad target. You weighed 170 pounds, depending on your height, of course, and all sorts of other things. Suppose the first time you got on it, it said 170 pounds. Then you stepped off and you got back on it, and it said 170.1. You stepped off it and got back on it, it said 169.9. Well, that's a fairly precise scale. And if it were accurate, that is on average, in this case it's on average 170, then that would be a good measurement system. If, however, you stepped on it and it said 170, and then you stepped off and you stepped back on and it said 192, and then you stepped off and you stepped back on and it said 148, even though on average it's 170, you might not feel too comfortable with that, because in practice you don't want to have to step on the scale 3 times. You just want to do it once and be done with it, and know that over time it's going to average out to be correct over the time. So precision is a desirable characteristic. And finally, reliability is very important. And when we say that, we want the measurement system to be to not change depending on if I measure it or if you measure it or if somebody else measures it. We want to get the same numbers. I once worked with a client who was a healthcare client, and the Department of Insurance called them up and asked how many members they had in the state of Vermont. The problem was they asked 3 different people, and they all came up with very different answers, from 2,000 to 50,000. That was a major issue for that company. That's the sort of thing that you don't want to have happen. You ask 2 different people to do it, you get 2 totally different results, not 2 approximately the same, 2 totally different results. And the other thing is that we want it to be stable over time. We don't want this changes of this measurement system to change over time. If we put the same standard part on, like if I had a particular weight of, let's say I wrote to the National Bureau of Standards and they sent me a 10-kilogram weight, I'd want that to be 10 kilograms today, tomorrow, the next day, a month from now, a year from now, 2 years from now, 3 years from now, because that thing isn't changing, so I don't want my scale to be changing. Hopefully that makes some sense. There are other characteristics such as ease of access and availability and all that kind of stuff that are also desirable, but we're talking about the statistical characteristics. So accuracy and precision, I think that probably the best way to understand it is to start with something. Here's something. Let's suppose that here are these bullseyes. You're trying to hit the center. Okay. So if you were trying to hit the center, you would say that this person is both accurate and precise. He has a small spread, plus on average he's hitting that target. If we go down to the bottom right, oops, hello, whoops, sorry. If we go down to the bottom right, we find that this person here, on this one right here, this guy's precise. That is, he has a small spread, but on average he's off target. You see that? So that's not so good. On this guy, on average, if you average up all the positive and negative distances and all that, on average this guy is actually hitting the target, but he's not very precise. And then finally, boy, this guy's neither precise nor accurate. The interesting thing is a lot of times things are easier if you can work on a precision first. Unfortunately, precision is sometimes, in a process fix, that's sometimes the harder thing. But at least conceptually, you can see that if you have something that's precise, fixing that problem's pretty easy. It's maybe a small adjustment, like shoot down and to the right, as opposed to this guy where he's just all over the place. That might be a difficult thing to fix. Okay, so let's talk about accuracy and precision just a little bit more. And just to use the phrase, accuracy is measured by something called bias. If something has no bias, it is accurate. Okay, and a bias is just a difference from where that true value is supposed to be. We'll do an example. To measure bias, you have to have some sort of gold standard, whatever that means, whether you write to the National Bureau of Standards and get a 10-kilogram weight, or the 800 grit sandpaper or whatever, or you have an in-house team of experts that says, for example, this particular call is going to be scored as a billing call. That would be the gold standard. Precision is measured by gauge variation, and so we'll run gauge R&R studies to do that. And there are 2 characteristics about this. We'll talk about this later. Repeatability, which means the same part in the same person, you're making multiple measurements. Why wouldn't they get exactly the same measurement? Well, if it's not a repeatable system, they won't. That's obviously a thing that you want. And then there's reproducibility, which means different operators, same part. So if I give the same part to different operators, then they're going to measure it the same, hopefully, if a system has good reproducibility. Okay. And just to keep in mind, the difficult thing about all of these things is really the setup, just like designed experiments. And in fact, it really is a designed experiment. Sorry to scare you again. But you generally need production time, right? You need to prep personnel. Like if you have 3 operators, okay, well, I'm going to have 3 operators. I'm going to have 5 standard parts that they're each going to measure, and I want them all to measure them 3 times. Well, I might want to think about things like, Should the operators know which part they're measuring? No, they shouldn't, because if they do, the second time that they measure that part, they're going to know what they did in the first time, and they're going to record that. They're going to give the same answer. Should they know what other people got? No, they should be blinded to things like that. So anyway, keep in mind that I use the word part to refer to anything that's measured, but it could be a phone call just as well as it could be a plastic part. All right. One last thing before we do a couple examples, or one example. Conceptually, if you have never done this before, the difficult thing to remember is we're not looking for differences between the parts. We are looking for how well the measurement system is performing. So we actually do want to see significant differences between the parts. That's what a measurement system does. It separates out good parts from bad, or certain types of phone calls from other types of phone calls. That's what a measurement system does. If it can't do that, that's what we're really testing, to see whether it can. Okay, let's look at an example. The example that we're going to do is found in the data MSA flowmeter.xls, and in this case we have a standard tube, and it's repeatedly used over time to test a flow meter when the tube is hooked up to a known gas source. So there's some source of gas. Maybe there's, it's supposed to have so many pounds of pressure flow, and you hook up the standard tube, and so you know what the answer should be, and we want to see whether or not it is over time. So the first part we're going to do is we're going to do an accuracy study, and remember, this means on average, is it giving you the right answer? This should be a pretty straightforward. Analysis. It's really sort of like a one num one cat analysis, and I'll show you how in just a second. We already have that in Excel Stats, so maybe it's best to just do it in Excel Stats. Let's first open up the data. Should be for week 7. Okay, so I've opened up the data, and here it's measured over time. It would be nice if I would have said, what the day was, so we can see it's sequential, but we can. It's Monday, Tuesday, Wednesday, Thursday. Here's what the measurement number is, not too interesting. Here's what the reference value, so it's supposed to read 5, and here's what it actually read. So let's check to see if there's a bias here. All right. So one thing that we could do is we could simply give the data labels. That would be fine. Another thing that we could do, right? So we could do the following. We could copy. I'll show you what I'm going to do. We could stack the data like this. Maybe this is a better way of doing it. Yeah, I think probably the best way would be to simply look at. Let's create one more column. Sorry about that. Let me clear that out. And I'm going to call this the difference. Whoops. Hello. The difference. And I'll say it's the reference equals the reference minus the measurement. Now, if on average there's no bias, that is, if it's accurate on average, these should add up and be 0, right? They should sum to 0. But we can do a quick one num analysis. Got to have Excel Stats open, though. Okay. Okay, now I've got the Excel Stats open, and let's just take a one num, right? Because now it's just one number. And we can see quite clearly that by looking at the data, I don't know, let's make this go from just -1 to 1, and you'll see there ain't no way that on average that this is going to be 0. In fact, there's clearly a negative bias on this. So you can see that there's no way that on average that it's there. We will do a statistical test to prove that. But again, if you wanted to know exactly what the bias was, it looks like it's about -0.5, whatever the units are of the flow. And now let's take a look at, if we wanted to also write the, look at that interval, there's the confidence interval of that, and you can see that it's clearly, less than 0. One last thing, if you really aren't convinced by this, you can run the test, and you can see if it's, here we'll type in the hypothesis mu is equal to 0 versus it's not equal to 0. Oops, did I screw it up? I think I did. Yeah, you're supposed to be able to change the blue. I screwed up, sorry. You change the blue. There we go. And you can see, there it is. There's the p-value. Certainly very, very small. So there's no way. This definitely has a bias, and you would say that the bias is somewhere between 0.6 and 0.34 bias. Or if you wanted just to report one number, you'd report -0.48, I guess. -0.48. Okay, so that's it. I mean, there's not much more to this study than that. The one other thing that you could also look at is you could look at what the data look like over time, and you can see that this bias looks like it's pretty consistent. To make it maybe show a little bit more easily, let's go from -1 to 1, do the major unit of 0.25, and maybe in this picture it's a little bit easier to see that there's definitely a bias, because we want that to read on average 0, and it's certainly not bouncing around 0. It's certainly bouncing around some other value, around -0.5. So this would be an example where this flow meter needs to be sent back and calibrated again. If you find that there's a bias in, say, a people measurement system, that could mean that there's training. That could mean that some definitions are off. Those are some things that you look at. So that's it for bias. You can see how to do it in Minitab on slides 95 through 100. I'll just quickly go through them. There it is in Minitab, calculating the difference. Now I just say, hey, look at that, but now we know how to run tests. So we actually did one better. Okay, here's the one that tends to get people, and this is MSA Gage R&R. Anyway, here's the general way of doing it. Here's a procedure that can help you do it. So if you're planning on doing this, here's what you need to do when you want to run a continuous Gage R&R. So what we're talking about here is we're talking about a measurement system. I just used my pad here. I haven't been using this pad, but we're talking about a measurement system where my output, whatever's being measured, is a num. Okay, and in the place where it's a cat, we'll cover that in attribute measurement systems. So here's the way to do it. So you get 3 to 5 parts representing the typical full range of product variation seen in production. So let's do an example. So suppose you were looking at, let's do a manufacturing example first, and then we'll do something else. Suppose you're looking at, not manufacturing, but how about warehousing? Suppose you're measuring the amount of space used on a pallet. What you might want to do is you might want to get, you might want to have 3 of those parts be one that was stacked extremely high, so an extremely packed pallet, one that's sort of a typical pallet, and maybe one that's a very lightly packed pallet. Okay? You want to get 2 or 3 operators. And here you want to do the same thing. You don't want to get all the best operators or all the worst. You want to get members across it. So you might want to pick, one of your inexperienced, one sort of moderate experience, and one very experienced operator. And then you want to have them measure each part like 3 or 4 times. That may be difficult, so you may have to blind them to know which part they're measuring. Or instead of just creating one of those special parts, you might create 2 or 3 of things that are so similar that they're basically the same. Okay? So that's one example. Now, another example might be, maybe in an office, might be, suppose you're working in a in accounting, and you need people to be maybe or in billing, and you need people to be reconciling invoices. Maybe you give them, the parts might be a really simple one, a fairly complex one, and a super duper complex one. And the operators might be, again, same thing, inexperienced accountant to experienced accountant or clerk, etc. And then instead of having them measure the same part, you'd have sort of 2 or 3 really complex ones that are basically the same, 2 or 3 really simple ones that are basically the same, and 2 or 3 medium ones that are basically the same. That's how you do it. Okay, so here's what we do in a Gage R&R. What we do, remember, Gage R&R is about the variation. What we do is we break the total amount of variation into 2 things. We say it's equal to the measurements. This is just concept, okay? We say that the total variation is equal to the measurement variation plus the variation from everything else. That could be process, it could be parts, it could be people, it could be information, all sorts of things. And then what we're going to do is we're going to look at the proportion of this guy to the total, and if it's around 10 or if it's greater than 10 or 15%, it varies in the industry, but some people will say 10%. Some people have even said high as 20%. I would rather say 10%, and err on that side. Say if it's greater than 10% variation of the total, then maybe I can do something about the measurement system variation. If it is there, then what we want to do is we want to further break this up into, say, reproducibility and repeatability. So remember, the reproducibility comes from different operators or appraisers or whatever, and this is same operators, but when they're doing it multiple times. So if I'm one of the operators, you give me the same part. If I can't measure the same thing twice, if I get, say you give me a flow meter, and the first time I measured it was 2.7, and the second time it was 29.3, I probably have a problem repeating myself. So that's repeatability. Okay, so just with a little more feeling, reproducibility, same part, different operators. Repeatability, same part, same operator. All right, let's do an example, and then we'll do one more example to kind of drill it a little bit. So the first example we're going to do is MSA GRR, MSA GRR, Gage R&R. Okay, and in this case we've just got 5 parts representing the spread of a product. I'm going to call it the defect rate of a shipment of goods. So I might have, simple shipment, complex shipment. You got it. There's 5 of those. And then we have 2 operators were chosen for production. We'd like to have 3 usually, and each operator measured at 3 parts. So this means the total measurements were 30. So we made a total of 30 measurements. 5 parts, 2 operators, each measuring 3 times. Okay, and the data are in here. How do we analyze these data, and what does that get us to? Okay, so here is the data in Minitab, and we're just going to port that over to, here's the data in Excel. We're just going to port that over into Minitab. And see, I'm using Minitab 16. And we will do the analysis. So I'm just going to copy it, paste it into Minitab. There we go. All right, so now we're going to do the Gage R&R study. And to find it, the hard part of this is finding it, actually. Stat, quality tools, Gage study. Okay, and we're going to do a Gage R&R crossed. Now, why crossed? Well, there's basically 2 of them. Now I guess that we have an expanded one, but crossed and nested are the things. Nested, let me show you what nested means before I just go ahead and do this. This is given on slide 105. Nested here's an example of a nested design. I have a measurement, and if I only give parts 1 and 2 to operator 1, and I only give parts 3 and 4 to operator 2, I can't really tell whether it's the parts that were causing the spread. Let's suppose that operator 1 had a much greater variation than operator 2. I can't really tell whether it's the parts or the operator. Sometimes you have to do that, and then you don't have a choice, and you lose some ability to see, and you have to make some guesses. But in our case, we're going to give every part to every operator, so we have a crossed design. This is an example of a nested design. All right, so back to the egg. We're going to come back here, and yeah, one of the things that I like looking at is looking at maybe we should look at the data by part or by operator or by rep, and we'll see if there's where there's variation. That would be interesting. We want to see it by part, right? So let's take a look at that. How can we do that? Well, one way is to do a box plot by group. So if I do output by part, okay, that's actually good because it shows you that certainly we should be able to tell there's differences between these parts. It looks like it's tough to tell the difference between 1 and 2, and maybe 3, maybe 5 also. But definitely can tell 3 and definitely can tell 4. That's good. Let me now graph. Let's do this box plot again with groups, and I'm going to add another variable. And now I'm going to add operator. No, not there. I'm going to still graph my output, but now I'm going to graph the operator too. So I have operator within part, and we say we have operator 1 and 2. Well, look at this. There may be some difference there. Box plots aren't doing it for me. I think the problem with box plots is we just haven't measured enough with them. So hold on a second. It looks like I have done something to Minitab that Minitab doesn't really like. Close this graph. No. All right. I'm going to do instead oh, there it is. That's what happened. Put that guy back up. I'm going to do instead a individual value plot, and it's like a box plot, except it also puts just the dots for all of them. So it works basically the same. So part and operator. Now let's take a look. Well, yeah, so notice that it looks like we measured 3 times each part. Well, it looks like maybe for part 1, operators 1 and 2 had differences. And boy, look at this. For part 6 or for part 5, big differences between operators. So that's interesting. I'm not sure exactly what it says, but maybe I'll have a reproducibility problem. Okay, now let's take a look at, maybe I did like the boxes better. They were at least telling me something. Easier to read, Yeah, that's fine. Yeah, so look at that. This is very reproducible for one guy and not for the other, or repeatable for one. Now let's take a look at that same graph, but instead of operator, I'm going to look at it by replication. So this tells me a little bit about the repeat. And I'm not sure what that tells me really. But the first one and second one told me something interesting. I might look and see if, yeah, maybe operators really are different, so maybe repeatability will be an issue. It'll be interesting to find out. Let's do the analysis now. Okay, so quality tools, Gage study, Gage R&R nested. Okay, so first thing is we want the part numbers or batch numbers, that's part. Operators, that's operator. The measurement data is in output. Now you'll notice that we didn't have to enter in a standard value because we're only doing variation. For variation, we don't need to know exactly what the right value is. We just are looking at how much it varies. And we didn't have to put in the replicate information. Minitab will figure that out. Okay, so go ahead and click the Okie dokie button, the OK button, and we'll just see. The most important, it gives you a bunch of things here, but the most important thing to, the most important thing to keep in mind is this guy right here. You want to be looking at this, and you want to see, is this big compared to this? And the answer is, yeah, it's pretty big. It's just about as big. So the variation that's in the gauge is just about as big, not quite, but just about as big as a variation in the parts. That's not good. Actually, we want that to be much, much smaller. So it looks like that's something that we're going to be worried about. The second thing that we can see from this is, well, okay, so now that we've decided this is big, we need to drill it a little bit, and so we should look and see which one of these guys, repeatability or reproducibility, is big. And here, it's very clear that repeatability is an issue. Repeatability is an issue. So often, repeatability means that there's either one of or more of the workers who just can't get it right, or it means that maybe the gauge doesn't measure at all. If all the workers are having repeatability problems, that's a problem. Now, I think I can interpret that plot that we had before. But before I do, I'm going to go into the session window and show you basically all we're really going to do is look it up on here. And there's a lot more to it to Gage R&R, but I think this gives you the basics. Here's our part-to-part variation. It gives a little ANOVA table. Whoopee for that. What we really want to look at is this. Here's the Gage R&R, 34%. That's certainly bigger than 10%. So that means, yeah, we probably have to do something about it. What's the problem? Well, it's a repeatability problem. Okay, so what does repeatability mean? Well, that means if I give the operator the same part multiple times, he gets a different answer all the time. Yeah, that's a problem. So maybe this person doesn't know how to use the measuring system. Maybe the measuring system really is not good. It's technically not good enough. If it's a definition, maybe the definition is not very tight. It's hard to interpret. No, those are the sorts of things you would look in, try and fix it. Okay, so that's that. So that would be it. So you know, the gauge says here's what you need to look at. Here's what you need to try and fix, the repeatability. Okay. So that was that. Now, you know, so what would be the things that we could do? Here's some other examples that are given on slide 109. You know, there are different things that you could do. One is, if it turns out that everyone needs training, maybe not everyone does, but if it turns out that everyone needs training, that might mean that the gauge itself is bad, or there may be one or more people who really do need training. It may mean the SOPs are bad. However, one of the solutions that I once had when I worked at a company called Corning was we took multiple measurements. Well, we knew we had problems with the variation and we couldn't repeat, but if we took, say, 3 or 4, we got a pretty consistent average. So that's what we did. And it wasn't the most elegant solution, but you know what? It worked. And it was way better to have reliable data. Okay, let's do one more example. And this one is exercise 1, which is invoice reconciliation. So in this one, we can imagine that there's a department, say billing and collections, where they need to be looking at invoices and they need to reconcile certain invoices. So they use 3 different types of invoices were used as the standard parts, low, medium, and high complexity, and they felt that that measured the full range of production. They also looked at 3 auditors. They had an inexperienced auditor and a very experienced auditor, and I guess one of the middling. And all invoices were pre-audited by a team of experts who determined the true value of the reconciliation. So in this case, we could do a bias study as well. I'm going to leave that to you. The accuracy study should be pretty straightforward. You know, we'll do it because it's pretty straightforward. So we'll do it. Is bias an issue for this measurement system? And then we'll perform a Gage R&R. So the first step, I guess, is to open up the file. So here it is right here, invoice reconciliation. We've got the measured and the accurate and the actual. Let's do the bias study first. Well, we should look at the difference, right? Difference. And let's say it's the actual minus the measured. tells me the delta between. Okay, we want this to be on average the same, so we can take a look at this. And let's take a look at Excel stats. I like Excel stats for doing all this kind of stuff. I just think it's really easy to do. Okay, here we go. Just going to select all of that. And let's see. Let me start out with a 1 num. And we'll just look at that difference. Oops, I've got it selected now, don't I? Okay, so the question, here it is. Wow, there's a couple of honking outliers. Better check those out. Not sure what those are, but it looks like maybe on average there is a bit of a problem. Looks like there's more. I don't know, maybe that's a big 0. Hard to say. Let me see if I can get a little more detail. Yeah, it looks like it's a bit bigger. But there are a couple of honking outliers that could be certainly pulling the average way back. Let's take a look at that confidence interval for the mean. Well, yeah, it's overlap 0, so maybe if we get rid of some of these outliers that we really don't, then we really don't have a bias problem. So we probably want to check into those outliers a little bit. And one way of doing that would be to say, you know, let's look at maybe who was doing it or maybe which replicate. So let's go back to here. And let's just select all of these. And what I'm going to do is 1 num, 1 cat. And we'll just kind of look back through all of them. I want my num to be the difference, and then I'll look at by auditor. So, oh, this is going to tell the story right here. Look at that. My auditors, with the low, he's all over the place. Low experienced. The medium experienced is reasonable, and the high experienced is pretty reasonable too. If we wanted to look at that in more detail, we could do separate frequency charts, which would show this. You see that this guy's all over the place, but these two are pretty much on target. That'd be one way of looking at it. We could look at box plots. There you go. Okay, so the medium guy is not quite as good as the high accuracy or high experience guy, but pretty close. The low guy is just all over the place. So, and my guess is that these are the two outliers right there. So again, you know, if you did this in Minitab, you'd actually be able to brush and tell. Should be kind of cool. You know, in some ways, we're doing the Gage R&R anyway, aren't we? We're not quantifying all that stuff, but we're doing it right away. All right. Let me take a look at, see if there's any other things we can tell by invoice. That's which invoice? What is that? Oh yeah, if it's low, medium, or high. That might be interesting to look at. So let's take a look at that. Oops, I got rid of my 1 num, 1 cat. Why did I do that? I'm not sure. Yeah, I'll move that by invoice and see if there's a difference that's discernible. Huh. No. I mean, and this is what he's supposed to be measuring, right? Apparently, because he got it right. Oh, that's the high complexity. That's the spread. Yeah, so look at that. For high complexity, they have a big problem. Let's look at it again on separate frequency charts. Yeah. So on high complexity, there's a major problem with that. And I wonder if it's connected with the low experience operator. Probably is. All right, enough of this. Let's take a look in Minitab now. And we'll do this the other way. All right, so let's do a Gage R&R. Gage study, Gage R&R, crossed again. Part numbers are part, operator, operator. Measurement data is the output. Click OK. And let's see. Again, it looks like repeatability is our problem. And yes, we have Houston, we have a problem. look in here. Doesn't always turn out this way, but again, it turns out that the part of the contribution of the variance again is a major repeatability issue. So now we just have to kind of figure out, is it one operator or is it all operators? I think we've already established it's one operator who's doing this. If you want to get a total picture of this by putting it all in, let's make a box plot with multiple groups. What I'll do is we'll put in output by part and by operator, and this should help us see. Did I miss something when I put it in? Yeah, how come it didn't? Oh, yeah. Let me actually put in the right data into Minitab. Sorry about that, folks. All right, here's the data. That's better. Let's do stat. Helps to have the right data. Gauge R&R, crossed, and here we want, let me clear all this out, here we want, the part is the invoice, the operator is the operator, or the auditor, I mean, and the measurement data is the FD actual. There we go. And this actually is a pretty good, for the most part, is a pretty good measurement system. Can't be right. Oh. It's FD measured. It's what they measured. My goodness. The measurement is what they measured. There we go. Okay, so here the gauge does have a problem. It's maybe not as big as a problem in the last one. And it's not as clear whether it's just repeatability or it's reproducibility. So let's go take a look at that. Boy, I'm not on the ball today. There it is right there. Yeah, it's 18% as opposed to before. And yeah, our reproducibility is pretty good. Our repeatability is problematic. So let's dig into that a little bit. Again, we did already note that it was that one operator, but we should be able to see in the box plot that that's actually true. So let me clear this out again. The measurement is what we're talking about. And we want to look at the invoice, and we want to look at auditor. You know, we could look at the difference also. That might be interesting to look at. But here's just a look at the at the data, and you can see that for here we've got auditor and here we've got invoice. So the groups are the invoices. So, and don't ask me why Minitab did it in this odd order. It just did. But here happens to be the low invoice complexity. It looks like it's not that much of a problem for low invoice complexity. That guy's got a bit of an issue, and that's the low experienced operator. For medium, it's not so much a problem, but for high complexity invoices, boy, the inexperienced guy is just all over the map. So that's the thing that we need to be able to be working on is, you know, how can we either get them up to speed quickly, or maybe in our process we make a process fix such that the low experienced person never gets the high complexity things, that they work into it over time. So it does naturally lead to several possible process fixes. But exactly what process fix is up to you. All right, so again, sorry about that little Minitab mishap, but hopefully that makes some sense. The analysis really isn't that tough. Just do a gauge R&R, see what percent is big, if at all. If it's less than 10%, you're good. If it's above 10%, see if it's repeatability or reproducibility, and then move on. If it's a bias study, you just look at the difference between the action, what it should be and what they got, and see if on average that's equal to 0 versus it's not. Simple hypothesis test. Okay, so hopefully you would agree that we talked a little bit about the MSA and it's important. Hopefully you're in agreement that it is important to have reliable, accurate, precise data. We did talk about the difference between accuracy and precision. Again, remember, accuracy refers to the average, precision refers to variation. And we talked about the various components of measurement systems variation, particularly repeatability and reproducibility. And hopefully we gave you a flavor of how to perform it. Remember, the hard part is to get the setup in the business setting. So try your best to get like 3 parts and 3 operators and have them look at it like 3 times. Rule of 3, you know. That works pretty well. Okay. Take care. Hope you found this helpful and illuminating. And let me just go to the front page here. We'll end it on the front page. Oh my goodness. And hopefully you'll be willing to try out measurement systems analysis. Very helpful.